Hello, people. What is up? How is everyone doing? Welcome to the session. What's up? What's up? What's up? I welcome you all to today's session, people. I hope you're having a fantastic day so far. My name is Anoop and this is Vedantu. And yes, today we'll be doing some short questions of magnetic effects of electric current. I'm hoping that you guys can hear me and see me clearly. Unfortunately, I'm not able to see your chats. Just give me a second, people. For some reason, I'm not able to see your chats at all. Just give me 1 second. Let me just sort this out. All right. Yes. Much better. What's up? What's up? Bhaiyo aur behno. Yes. Ladies and gentlemen, boys and girls, how's it going? How's your day so far? All good? Hello, hello, hello. Yes. My voice is low. आपके टूथपेस्ट में नमक है? No, unfortunately not. In my toothpaste, I have Abhishek sir. Abhishek sir. Guys, is it better now? Is it better now? Should I put on my earphones? Is it better now? Yeah, I look so cool. I look like a DJ now. Is it better now? Is it better? Unfortunately, guys, I'm in a different place right now. So yeah, I know. I'm actually in a different place. So please adjust for today. And like I'm actually traveling for that reason. But yeah, at least you guys can hear me. No, no. Still, is it bad? Is it still bad? Look at me. I look like a DJ. I just need a disc. That's all. I'll just take a random CD drive and start rubbing it. That's all. That's all I need to do to look like a DJ. All right. We can hear you, know? All right. Awesome. 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 Thank you, people. Thank you for that. All right. So, anyways, a very warm welcome to all of you guys out there. Today, we're going to be doing, magnetic effects of electric current, and it's hosted by none other than DJ Anoop Sir. And we'll try to do our very best to get through all the questions that are basically short questions or guaranteed questions for term 2 examinations from magnetic effects of electric current. So we'll try to cover as many questions as possible. And I have once again divided the questions into three different categories. So we'll start with the 2 mark questions, which would be quite straightforward. And all of the questions today are going to be from previous year question papers itself. None of the questions would be from random sample papers and all. Every single question has been carefully chosen because they have been taken up from the previous year question papers all the way from 2010 to 2017, 2018. We have questions from all over the place where, wherever these kind of questions have been asked from magnetic effects of electric current. So we'll start with the 2 mark questions, which would be quite easy. Then we'll move up, we'll step up to 3 mark questions. And then finally, we'll land our punch with the 5 mark questions. All right. Can I get a oh yeah in the chat box, people? Yes, yes, Nipunji. Yes, yes, we'll definitely have it. All right. Yes, I know. DJ Anup is cool. I know. I think. How many of you guys want me to see like this every day? How many of you guys would like to, like me to be like this, like wear earphones and all, pretend like I'm just talking, like like do this, yeah, every day, man, every day. I actually look like a DJ when I do this. Look at that. Chick, chick, chick. And yeah, this is YouTube. It's gonna be on the internet forever. I'm gonna have memes of this now. Alright, so anyways, let's get started, guys. Let's get started. I know. That why this the big white was awesome. Alright, so anyways, let's get started. Guys. Let's get started. We'll start with the 2 mark questions, work our way through 3 mark, and then we'll move on to the 5 mark questions. So the first 3 mark question is actually appeared in 2014 board exam and 2015 board exam as well. So it's basically related to magnetic field lines. So you have 2 parts of this question. One part of the question was asked in 2014 and the other was asked in 2015. So here's the question. How do you define magnetic field lines? That's the first part of the question. And you have to justify the following statements. The first statement is two magnetic field lines will never intersect each other. All right. Again, it's a 2 mark question, so each of them would carry 2 marks. And last but not the least, magnetic field lines are closed curves. You have to justify how are they closed curves. All right. Super easy question, people. Super duper. I mean, it's a simple start, though it's not really that difficult of a question. So let's start with the first basic question. What are magnetic field lines? How would you define magnetic field lines? Saketji, unfortunately, we don't have Mentina because you're gonna give your subjective exam another month or two. So yes, focus on that. Menti itself. Uh-huh. Or exactly, Kushagra, exactly. It's nothing but the representation of the magnetic field around the conductor or around the magnet. So it is nothing but Magnetic field is nothing but imaginary lines. See, there are different ways to define it. You can define it as magnetic field lines are nothing but those lines which represent how the magnetic force is acting around a magnet or a current carrying conductor. That is one way to do it. Another way to define the same is basically you can say that magnetic field lines are nothing but the representation of the north pole of the magnetic field. So basically, the magnetic field lines move from north to south, right? So the representation of the north pole of the magnetic field or magnetic force, that is what is shown by your magnetic field lines. Or you can also say it as it is nothing but the imaginary lines, which is a representation of the magnetic field around the conductor or around the magnet. So that's basically it. But yeah, again, whatever definition you choose, you have to make sure that you are very elaborate about it. It's a 2 mark question, so you don't have to write what is that? So, all sorts of stories and stuff. Keep it simple, but write down the keywords. That is very important. Okay. Now for the 2014 question, guys, the first question for today. The magnetic field lines never intersect each other. Now the question is very clear that magnetic field lines never intersect each other. Now you have to justify why is that not the case. Like why don't they intersect each other is the question. It's not that whether they are intersecting or not. They are never going to intersect. The question is how do you justify that they are not intersecting with each other. Hi Prathamesh, what's up, Dab? Sir, if they would intersect, exactly, Kushagra, exactly. So there are two ways to define this, people. Again, it's a 2 mark question, so I would suggest you to write both of them. So the first reason would be that if you were to place a compass exactly at that interjection, what would happen is that the north pole of the compass would point in two different directions. Now you can't have two different north pole at the same point, isn't it? So that is one reason. Another reason that you can say is that if you were to draw a tangent, right? Now the tangent over here also would point in two different direction. Now you can't have a tangent in pointing in two different direction, which means you have two different north pole. Now you can't have two different north pole, and for that reason, physically speaking, no two magnetic field lines can intersect each other. All right, we are talking about the same magnet. For the same magnet, no two magnetic field lines would never intersect each other. So that is the answer for that question. All right. Okay. Second part of the question: magnetic field lines are closed curves. Now again, this you have to justify how they are closed curves. So I would suggest, since it's a 2 mark question, I would suggest you to draw the diagram, the magnetic field of a bar magnet as well, just to just to be cleared, so that there's no way that they're going to deduct your marks. So I would suggest you to draw the bar magnet and draw the magnetic field around a bar magnet as well. So please draw a bar magnet over here. So once you draw that, you can just define it in your own words. So magnetic field lines are closed curves because they are nothing but closed continuous curves. So outside the magnetic field lines start from the north pole, end up in the south pole. But inside the magnet, however, so if this is the bar magnet, they start from north to south. Let's say this is the north pole, this is the south pole. But inside the magnetic field lines are going from south to north. So it's a continuous, closed, continuous loop or curve which starts from the north pole on the outside, ends up in the south pole, and then on the inside, it starts from north all the way to the south. All right, sounds good, people. Makes sense. Super easy question. Again, 2 marks, easily. You can score it. You don't have to do anything. The basic stuff is all you need to remember, and you're good to go. Sounds good, people. Yes. Exactly. So by the experiment, you can use anything that you want. See, magnetic field lines you can show through solenoids also. Absolutely fine. There's nothing wrong in it. Whatever you feel is more easier, you can go with that. I would go with bar magnet because you've already seen it, and more importantly, it's one of the most clearest representation of magnetic field lines. So I would generally prefer the bar magnet. But again, you can use a solenoid. There's nothing wrong in it because the magnetic field in a solenoid and bar magnet is very similar to each other, so it really doesn't matter. All right. Okay. Yeah. I mean, you can for a straight current carrying conductor, you can say that the magnetic field lines are concentric circles. You can do that. You can absolutely mention it, but when you're defining it, you can just define it using this one. I would say define with the bar magnet, because over here, when you talk about this also, there's no clear representation. We have not spoken about. You guys know that if current is going in clockwise direction, then it's north pole, anti-clockwise south pole. So there's no like clear representation as such. This is a clearer representation, I would say. This is a much more clearer representation of how the magnetic field lines are starting from north, ending up in the south, and then going from south to north. So I would suggest you to go with bar magnets here. It's not that it's wrong, it's just that here there's no clear indication of which is the North Pole and South Pole and how they are exactly closed curves. All right. Even solenoid also is a good choice. That solenoid or bar magnet would be a better choice because it's a clearer representation of the magnetic force and the magnetic field lines. All right. Okay, so you get the answer for this, people. The whole answer is given over here. You can download the notes later. Let's go on to the next question. And this particular question has been asked 3 years back to back, 2011, 2012, and after 2 years, where CBSE decided, let's surprise you people. And 2015, surprise, surprise, it's back. So the question is, guys, a metallic conductor is suspended perpendicular to the magnetic field of a horseshoe magnet. All right. So you have a conductor which is placed in a horseshoe magnet. The conductor gets displaced towards the left hand side when current is passing through it. What will happen to the displacement of the conductor if current through it is increased? That's the first part of the question. Second part of the question is, if the horseshoe magnet is replaced by another stronger horseshoe magnet. And last but not the least, if the direction of current through it is reversed. Let's start with the first question, guys. If I were to increase the current flowing through the conductor, what would happen to the force acting on the conductor? Exactly, guys. Now, first of all, before I get into that, tell me, guys, what is this force called as? What is this force called as? Hi, Neelam, what's up, da? What is this force called as? So, for Monday, my pre-boards are going to start. Uh, Faizan, I would say pretty much all of the topics are important. But if I talk about, I'll tell you that towards the end. All right, please remind me this question towards the end. I would definitely answer it. Exactly, guys. It's called as Lorentz force. And if you remember, the Lorentz force that you have is actually there's a formula to it. Lorentz force. There's a formula to it. So the formula is F is equal to BIL. Right, BIL sine theta. Let's just keep it as BIL for now. So which means that if force is directly proportional to the current. If the current is increasing, obviously the force on the conductor will also increase. Yes, that's the first part of the question. Second part of the question: if you were to replace the horseshoe magnet with a stronger one, much stronger one, what would happen again? Again, the force would increase. Why? Because force is directly proportional to the magnetic field. So if magnetic field is more, force would also be more. Jujube, no? Last part of the question is, if the direction of current is changed, if it is reversed, then what would happen? If direction of current is changed, then what would happen? Hi, Shivam. Good afternoon. What would happen? Think, people. If direction of current is changed, what would happen to the force acting on the current carrying conductor? Again, jujube question. Jujube question. Yes. Exactly. It's not the force acting on the conductor would also change. See, initially here the conductor is going towards the left. So if you change the direction of the current, now the conductor will move towards the right. Because according to Fleming's left hand rule, the thumb shows the direction of force, the index finger shows the direction of the magnetic field, and the middle finger shows the direction of current. And hence, people, it's going to now go towards the right and not towards the left. Make sense? So if the direction of current is changing, the direction of force acting on the conductor would also change. Why? Because Fleming's left hand rule. That's it. Exactly. Got it? Clear? Super easy question. This question has been asked three years in a row, 2011, 2013, and 2015 as well. So yes, pay attention to these kind of questions. They might ask you the same type in a different manner. All right? Because CBSE likes to put googly balls like this. All right? Okay, guys. So that marks the end of the 2 mark questions. Let me ask you a very serious question. Very serious question. How are you guys feeling right now? Yes. Josh is still high, or Josh has died down after seeing the first part of the questions? How's it? I can't see my phone now. Like I told you, I'm in a different place, so I just like adjust. I just do a lot of jugards today. Yes. Hi. Are Neelam J. That's the spirit. Josh is high. Interesting. That is what I want to hear. No low Josh at all. Low Josh has to run out. But high Josh is what we expect over here. All right. So let's get on. Enough that too much. Okay. Now let's go on to the 3 mark questions. Now 3 mark questions would require a little more deeper explanation of the concepts. If they've asked for a diagram, please do it. If they've not asked for it, I would say still do it, because if the definition is quite small and you feel like it's not up to your 3 mark, if it's not worth 3 marks, then I would say please draw the diagram to make up for it, because that would give you an edge over, about edge in the sense like you would have a better chance of getting the whole 3 marks. All right. So here's the first one, guys. Again, two times, 2014, 2016 board exam. All right, so quite recent. So here's the question. List four factors on which the magnitude of magnetic force acting on a moving charge in a magnetic field depends on. What are the four factors on which the magnitude of magnetic force, the magnitude of force acting on a charge depend on? Super easy question, guys. Super easy question. Exactly. But that's only three, Shivam. That's only three. See, F is equal to BIL is absolutely correct. So, which means that force acting on this charge would be directly proportional to the magnetic field. Absolutely, yes. There's no denying that. More the magnetic field, more the force acting on the current carrying conductor. F is directly proportional to the current as well. Greater the current, greater the magnetic force. Again, there's greater the Lorentz force. No denying that. And F is directly proportional to the length of the conductor, which means the longer the conductor, that is, the more number of turns that you have, the greater would be the force acting on the conductor. The longer the conductor, the greater would be the force acting on the conductor. All right, there's no denying that. But there's one more thing that matters. Yes, L is nothing but the number of turns here. L here is nothing but the number of turns. All right, here L is nothing but the number of turns. Basically, more the number of turns, more is the length of the conductor. That's quite simple. What is that other factor that it depends on? That is what I want to know. I know that you would have gotten all these three correct, but there's just one more factor because they've asked for four factors and not three. What is that other factor? Not the radius, not the area. How is resistance different from resistors? Resistor is basically the device. Resistance is nothing but the obstruction. Answer is, see guys, the actual formula is F is equal to BIL sine theta. So the angle between the magnetic field and current is also a deciding factor. The angle between the magnetic field and current. If magnetic field and current are at 90 degrees to each other, then the force will be maximum. If they are parallel to each other, then the force would be zero. Zorro, it's a Zorro, the hero. Okay, zero. Getting it? If they are both parallel to each other, it's zero. So the angle between the magnetic field and the current, that is also a deciding factor. All right. Now, see, guys, let me tell you one more thing. This is not the only formula. All right. There is another formula as well, which means that the force that is acting on a charge is also dependent on the magnitude of charge. It is also directly proportional to the velocity of the charge, how fast the charge is moving. It also depends on that as well. But this is something that you'll study in your 12th standard, in your higher grades. All right. So some textbooks, some places, like even if you search on Google, no, you might get answers like this. But I would suggest, because it's for 10th standard, I would suggest to go with this one itself. F is equal to BIL sine theta. That's more apt here. It's not that this is wrong, but that is something that we have not gone through as of now. You will be studying about it later on. So the magnitude of charge, the velocity of the charge, all of these are also deciding factors. But let's not get bogged down by that, because right now we don't have to deal with that. Sounds good, people? All good? Yes, people? No. And so that is the best part about this, people. Even though you have a formula F is equal to BIL sine theta, there are no numericals based on this. All right. All you have is these kind of relationships. So if you're able to remember that, you're good to go. All right. There are zero numericals in this chapter. Zero numericals. You just need to know your hand rules and one formula, and you're good to go. All right. Okay. I mean, theories though is there, working of motor and all that. Don't get me wrong. But in terms of numericals, whoever loves maths a lot, who would like to, hug math and sleep tight in the middle of the night, like there are people over here, I'm pretty sure, who have dreams of math, right? Like who wake up in the middle of the night sweating because you've been doing a math problem. I know. So for you guys, it's a good news. All right, love math, no? Huh? I'm talking. It was sarcasm, guys. Sarcasm. Hashtag sarcasm. All right, it's sarcasm. Basically, what I'm trying to say is why do you wake up sweating? Because it's a nightmare. No, understand sarcasm also. 10 standard, no. Is it 10 standard? No. What is this? Sarcasm also you don't understand all. Every time I have to write it on a sticky note and stick it on my head or what? All right, okay, let's go on to the next question, guys. This is another one from 2016. How will a fine beam of electrons streaming in west to east direction be affected by a magnetic field directed vertically upwards? Explain with the help of a diagram mentioning the rule applied. My God, this is an amazing question. Amazing question. So go ahead and answer this, guys. How will a fine beam of electrons streaming in west to east direction be affected by a magnetic field directed upwards, vertically upwards? Explain with the help of diagram mentioned the rule applied as well. Super easy question, 3 mark. This is for 3 marks. I mean, it can't get any more easy than this. But again, you need to know your hand rules. Okay, let's start with the first question. Which hand rule would you apply here? Which hand rule would you use over here? Let's start with that question. Simple question. Exactly. Arre, Tanvi, right and thumb rule. De, addi. Exactly, Kushagra. Exactly. It's not the right and thumb rule, guys. Please don't get this wrong. It is Fleming's left hand rule. Fleming's left hand rule. Left hand rule is the one. All right. FLHR, which is nothing but Fleming's left hand rule, is the one because we're talking about a beam of electrons. Right hand thumb rule only tells you the direction of the magnetic field around a straight current carrying conductor. It doesn't tell you about anything else. The left hand rule, Fleming's left hand rule, is the one that is actually used over here. So according to Fleming's left hand rule, when you take your left hand and extend your middle finger, index finger, and thumb such a way that they're all perpendicular to each other. The thumb shows the direction of force acting on the conductor, the index finger shows the direction of the magnetic field, and the middle finger shows the direction of the current flowing through the conductor. Now, here is the thing, guys. You tell me in which direction the force acting on these electrons would be. You tell me. I'll give you guys 10 seconds time. आराम से do it, all right? But I want every one of you guys to try your very best. When I say the best, I mean the best of the best of the best. Inwards, pakka, 100% inwards, out of the page, adipoliya. Thank you. Fleming's left hand rule, all right. In the page, sure. Not towards us, all right. That means away from us, all right. Yeah, write this. Write it in exams. Like when they ask this question, no, not towards me, towards you, not towards me. What? You have to mention the technical terms out of the page. All right, okay, let's try to do this. See, guys, the first major mistakes you guys do is this. Electron beam is going from west to east. West is basically my left or your left to your right. All right, so electron is going from west to east. That is shown by a middle finger. Now the thing is, guys, if electrons are going from west to east, what is the direction of current here? What is the direction of current? If electrons are going from west to east direction, what would be the direction of current? Current. Where is the conventional current? Opposite, exactly, east to west. So middle finger will point from east to west direction. Now, middle finger, east to west. The magnetic field is going upwards. So what is the direction of force? It is into the page. It is away from you and towards the screen, which means it's into the page. Every time, please remember these things, guys. Remember this, very, very important. If it's away from you and it's pointing towards the screen, that is into the page. That is into the page. If it's coming towards you, then it would be out of the page. So here in this case, it's going to be into the page, or in other words, you can write it as north, because if this is east, this is west, in front of you is north, you are south. So behind you is south, in front of you is north. So you can either write it as north or you can write it as into the page. All right. So that would be the answer. Make sense, people? Understanding? So please remember this, people. If they have mentioned electrons, you have to take the opposite direction. That's not always the case, all right? If they have mentioned electrons in particular, then take the opposite direction, because conventional current always flows in the direction opposite to the flow of electrons. So please remember that, all right? Very important. I know that a lot of you guys would have made mistakes over here, but it is very, very important, because that silly mistake, that one little mistake is going to cost a lot. Question. All right. Lot of lags. I'm sorry, guys. I'm sorry. Yes, I hope it's yes, MVQ of today, because this question has not been asked once, not twice, not thrice even. Definitely not 4 times, not 5, but 6 times. 2010, 2011, 2012, 2014, 2015, and 2016. 6 times this question has been asked. 6 times this question has been asked. Time and again, this question has been repeated so many number of times. The question is very simple. What is a solenoid? Draw the magnetic field lines due to a current carrying solenoid. Write 3 important features of magnetic field obtained by a solenoid. Each part would carry 1 mark. So definition of solenoid gives you 1 mark. Drawing the magnetic field will give you 1 mark. And last but not the least, writing about the features would give you another 1 mark. 3 marks in total. 6 times this question has been repeated. That is just fabulous. All right, so go ahead and write this, guys. What is a solenoid? Let's start with that. What is a solenoid basically? How would you define solenoid? Exactly, Anshika. Exactly. A solenoid is nothing but, guys, it's nothing but insulated copper wires which is wound to look like a cylinder. Or you can say it's nothing but a collection of circles, collection of insulated n number of insulated copper wires, circles of insulated copper wires which are put together to make it look like a circle. That is what is a solenoid. Now, what does the magnetic field around the solenoid look like? The definition part, again, you can download the notes later. That's why I'm not writing it down, because I want to keep it short and sweet. But let's talk about the magnetic field lines, guys. How do the magnetic field lines look like when you talk about a solenoid? Why do we usually copper? Because copper is a good conductor. You could use silver, but that's what, if you're part of the Ambani family and all, then yes, absolutely use silver, gold. And if you can donate some to me also, I would absolutely love it. I take charity like this all the time. I really don't mind. Absolutely fine. You can donate. I'm absolutely fine with that. Yeah, yeah, sure. I don't say no to charities because I'm a good boy like that. Okay, exactly, guys. It behaves like a bar magnet. Absolutely correct. It starts. It is very similar to that of a bar magnet. You'll have a north and a south pole. The magnetic field lines start from the north, end up in the south. So yes, it is very, very, very similar to that of a bar magnet. So that is also done. So I just write it as bar magnets because I hope it'll make sense while you're going through the notes later. So the magnetic field lines around a solenoid look very similar to that of a bar magnet. Now tell me 3 features of the magnetic field lines. Now this is by far the most interesting question of all the 3, because the first 2 questions are very straightforward. But tell me 3 important features when you look at a solenoid that you feel like it's standing out, which makes it unique from all the rest. What is it? Solenoid, parallel, exactly, inside the, so you have to mention that inside the solenoid the magnetic field lines are parallel to each other. What does that mean? Since they are parallel, you can say that the magnetic field is uniform, and it is also very, very strong inside the solenoid. Inside the solenoid the magnetic field is going to be uniform and it's going to be strong. So that's the first part. Now outside, what does the magnetic field line look like? Outside, very simple, guys. How would the magnetic field lines look like? Very simple. Go quickly. Adipoli means nice, da. So from all Faizan, I'll definitely answer it. Don't worry, da. Happy Holi to you guys as well. Exactly, it's going to be closed continuous curves, which basically starts from the North Pole and end up in the South Pole. Last property, one of the other things that really stands out of a solenoid is what, people? One last thing, they are closed curves, absolutely fine. But what is that one last thing that makes a solenoid so much more different from that of a bar magnet? Yes, exactly, Asha. Exactly. So here, no, in a solenoid, if current is going in clockwise direction, that is the south pole, and if current is going in anti-clockwise direction, that is the north pole. So magnetic field lines are going from north to south, from clockwise, wherever the direction is clockwise, to wherever the direction is anti-clockwise. All right. So that's how it's going to be. Or sorry, anti-clockwise to clockwise. What exactly, guys? Exactly. That's what I'm talking about. Exactly, Anand. Exactly, Nipun. See, guys, in a solenoid, one of the most important feature is that the polarity is not fixed. You can change the polarity whenever you want, depending on the direction of current. If you change the direction of current, the polarity would also change. That means initially it was north pole. If I change the polarity, then that will become the south pole. So that is also one more key feature that makes solenoid so much more different from that of a bar magnet. You can also add one more thing if you want, guys. You can also add the directive properties. Uh, I don't know if you guys remember, in your 6th standard you had studied that if you take a bar magnet, tie it to a thread and suspend it freely, the magnet will automatically rest in north-south position. Right? You would probably study. I don't know if you guys remember this. You had studied this in your 6th grade. There was a small little experiment that you had done. Do you guys remember that? So that is called the directive property. For example, if I take a solenoid, all right, and I were to suspend it freely, this directive property would also be applicable for a solenoid. So this will also point in the north-south direction of the Earth. All right. So that is also one more key feature when it comes to solenoids. All right. So that these are all the key points. You can write it down. Again, you can download the notes later and take it down for yourself. All right, guys. So three more questions done. Tell me, people, how's your confidence level now? Has it gone up, or is it has it come down a little now? I'm from Bangalore. Study, unfortunately, no, there's no mentee today because today is going to be all subjective because you're going to give a subjective examination. So I want to give you guys as much training as possible before you get onto the battlefield and start ripping those question papers apart. All right. No, I'm from Bangalore. I'm from Bangalore. Yeah, hi, still. Ah, give me that fire wala symbol if you're, you know, give me the fire wala symbol if your Josh is still very high, burning like a ever burning inferno or tornado, whatever. No, I'm not from Andhra. That's what I'm trying to tell you. I'm from Bangalore. All right, yes, that's the spirit. People, give me a high five. That's it. Hi, Akshata. What's up, there? Hi. Why do you have to do this? Huh? Why do you have to do that? Anyway, so let's get into the topic. Let's get into the topic. The last and the final question, which is a straightforward 5 mark question. You know where questions come. See, guys, in magnetic field, there are two questions where you can get can be asked a 5 mark question. One is the working of a motor, and the other is either the right hand rule, thumb rule, left hand right hand thumb rule, or left hand rule, or right hand rule. So any of these things can be asked as 5 mark question. So the hand rules, I would classify it as one type of questions. Then working of motor is another 5 mark question, which you should definitely know. Working principle, the construction of motor is a short question. So please do not ignore it at all. With that said, here is one question for you people. Apart from that, here's one. Describe an activity to explain how a moving magnet can be used to generate current in a coil. This question was asked 3 times: 2012, 14, and 15. Again, very important. So let me see how many figures can answer this one. It's a 5 mark question, which means that just by writing a one line answer is not going to cut it. If you want that 5 marks, you have to be as detailed as possible with diagrams, with explanation, with as much content, as much relevant information as possible. You need to put it down in order for you to score, in order for you to secure all that 5 marks. So with that said, let's go ahead, people. Come on. Sure, Sakya ji, absolutely. I would love dum biryani for sure. Exactly, guys. This is nothing but electromagnetic induction. They are talking about EMI. Okay, now tell me in simple words, how would you define electromagnetic induction? In simple words, how would you define electromagnetic induction? In your own words, how would you define electromagnetic induction? Absolutely, there's no doubt about it. This is nothing but electromagnetic induction, also written as EMI. So the activity they're talking about here, they're referring to here, is definitely electromagnetic induction. Take a solenoid and a permanent magnet and move the permanent magnet. And yes, exactly, guys, exactly. See, exactly. The relative motion, right? So these are the keywords. When you have a solenoid or a conductor, and you have a magnet, and when you move this magnet that is linked to the conductor, there is a voltage induced in the conductor. That induced voltage is what is called as electromagnetic induction. Because of that induced voltage, there is current flowing through it, and this current can be detected by using something called as a galvanometer. So if you connect, so you have to draw the circuit also, guys. It's very important that you do it. So what you do is that for this, I would say, draw a solenoid, connect a galvanometer to it, which is generally just a G, that's all, and then keep a magnet near it. So what would happen is that when you bring the magnet closer to this solenoid, there will be a deflection in the galvanometer. Why? Because there is current induced in the galvanometer because of the relative motion between the conductor and the magnet. Relative motion means with respect to the magnet and with respect to the solenoid, how they are in motion with each other. So for example, I can keep the solenoid constant and I can move the magnet, or I can keep the magnet constant and move the solenoid. But nonetheless, when there is a relative motion between each other, there is a voltage induced, there is a current induced in the conductor. That is what is called as electromagnetic induction. And one of the best diagrams over here is this. Just directly do this, because this is one of the first things that you'll study in EMI. That is about Faraday's law of electromagnetic induction. So just draw the diagram, show the deflection, and write it. Again, it's a 5 mark question, so I would ask you to do this as well. So you can mention this, that when the magnet is moved closer to the solenoid, there will be deflection in the galvanometer. But the minute you stop it, the deflection will come back to zero. Again, when you move the magnet away from the solenoid, again there'll be a deflection, but this time the deflection would be in the opposite direction. And the minute you stop it, again, when the relative motion between each other becomes zero, then the galvanometer will come back to zero again. So there always has to be a moving magnetic field, a changing magnetic field, in order for you to witness electromagnetic induction. All right, guys, make sense? So yeah, momentary deflection. Yeah, you can mention the word momentary deflection, which means it's only going to be for a couple of seconds. It's not going to last forever. It's only going to be for a couple of seconds, and then immediately after, it's going to come back to zero. All right. So that's pretty much it, guys. That was the 5 mark question. It was asked in 2012, 14, and 15. We're not done yet. For sure, we're not done yet. We have a long way to go. I'll be coming back with the Sprintex series pretty soon. The Sprintex series would be for the electricity would be starting this week. Sometime during next week it'll be premiered. Magnetic field will be starting the week after that. We'll be going through that one as well. So for now, that's pretty much it. And yeah, if you have any doubts, anything that you would like to ask me, please reach out to me. This is my email ID, anup.manoran@vedantu.com. And this is also my Instagram handle. If you guys want to follow me on Instagram and, talk to me over there, absolutely fine. I always welcome that. Anup_Vedantu. So that's pretty much it, guys. If you have any doubts, do let me know. And yeah, so do CBSE know full EMI full form. Alright, they made the question. They have designed the whole thing. What do you think? What do you think? Alright, sure, Devaji, sure. So from Monday, oh yeah, Faizan, I would say that for electricity chapter, see guys, if your pre-boards are approaching now and you're like really not sure where to start, I would say for electricity, please, go through all the numericals, the current formula, electricity formula, voltage wala formula. My God, electricity itself. Electricity, that's the chapter itself. So current is one thing. Remember the formula for voltage. Then apart from that, the formulas for Ohm's law. That's another thing that you need to remember. Then apart from that, the parallel series connection. So series and parallel combinations, the combination of resistance, very, very important. Then apart from that, power and heating effect. So these are all the questions that you should focus on in electricity. Again, based on all of this, you might have numericals, so please do focus on that. When it comes to magnetic effects, I would say magnetic effects, remember all the hand rules, super important. Focus on all the hand rules. You have to be very clear about using the hand rules. You have to be thorough with that. Then apart from that, what I say, remember all the theory that we did just today, whatever theory questions we did, go through that as well. And apart from that, remember the working and working principle and the working of a motor. So these again hand rules, the questions that we did today, solenoids and straight current carrying conductor and circular loop and what to say. Apart from that, electromagnetic induction, EMI, all of these also you have to cover along with basically the entire chapter itself. There's nothing left out, but all of these are important because there are only 2 chapters in physics, and you never know where they're going to ask the questions from. So it's better to be prepared for all the topics. All right. So EMI is economics. I know. EMI is, yeah, I know. It's what is that? Monthly installments. Easy monthly installments or something. No. Okay, don't write it as EMI then. Write it as electromagnetic induction instead. All right. Happy now? Happy? That's all. Just do that. All right. So, anyways, guys, exactly. Everyone. All the best for that. So that's it from my side, guys. Thanks a lot for joining today's session. I hope you enjoyed it. If you did, do not forget to, hit the like button, like Toko, subscribe Toko, and bell icon भी ठोक दो, सबको ठोक दो, न्यूज़पेपर को भी ठोक दो, और ये रांचो शीट को भी ठोक दो अपने शीट से. That's it. All right. So Toko, like. I'll catch you guys later. I'll catch you guys later. Take care of yourselves. All the very best of luck and good luck. Stay safe. And I wish you guys all the very best of luck. That's it. Yeah. Peace. Take care, guys. Bye bye. See you all. Take care. Bye. Enjoy yourself. Have fun. Bye.